Ladies and gentlemen, welcome. This is our fourth seminar of 4ST441 Statistical Methods and Capital Markets. Today we will speak mainly about analysis of dependence, analysis of correlation or autocorrelation in the data set in a time series. We will speak about a lot of tests and a lot of methods for analyzing of dependence. So I hope that you are ready and we can start. Dependence, autocorrelation in time series of logarithms. Basic tools for exploring dependence. Autocorrelation is, for example, we can say luck plots. We can use sample autocorrelation function. We can use just shortcut AFC autocorrelation function. Different types of tests of independence. Maybe you know well-known Durbin-Walson test, the Durbin-Walson test statistic, Breusch-Godfrey test, which is based on artificial regression of residual component or artificial regression, Ljung-Box Q test, which is based on correlation coefficients, and, for example, runs tests. The test designed on science. Yes. We can illustrate here luck plots. The luck plot is a special type of plot with the two variables where one is locked. Yes. So it means that there is one variable, yes, variable 1 and variable 1, but in time t minus 1. Or if you check this, there is variable y on observation e, and there is variable y, but on observation e minus 1. Yeah? So log plot. If data shows a linear pattern, it suggests autocorrelation is present. A positive linear trend, yes, it means going upwards from left to right, positive autocorrelation. A negative linear trend going downwards from left to right, as from left top corner to right bottom corner, negative autocorrelation. The tighter the data is clustered around the diagonal, the more autocorrelation is present. It means perfectly autocorrelated data well clustered in a diagonal line. There is another exercise. Use luck plots, means plots of the time series of logarithms against its locked versions to study both the linear and non-linear autodependence or autocorrelation in the time series. I will illustrate this test on prices of stock, prices of Coca-Cola company. So there is a sample size, yes, close prices in time t, and close prices in time t minus 1. So it's necessary to use the data set which I sent to you, yes, and this data set shift by one observation forward. As you can see, this value is written here. This value is written here. This value 285 is written here, 285. As there is value 282 and here, as there is a diagonal moving, yes, so shifted by one position. And according to this data set of prices and this shifted data set of prices, yes, in time, you can create a scatter plot, yes, x, y point chart, yes, for example in Excel. So the scatter plot is created here, where we have here variable y in time t, yes, here, and variable y in time t minus 1, yes, so locked value. And observations, yes, are here, and you can see the increasing trend of this development, where this trend is moving from bottom left corner, yes, to right top corner of this chart, yes. It means that there will be probably strong correlation, strong positive correlation, yes. So this is the case of prices, yes, original data. But we can calculate log returns, yes. We talked about log returns, and log returns calculated from prices, logarithm of price in time t divided by price in time t minus 1 is calculated here. And again, we have here a column with shifted values, yes. This value is shifted here, this value is shifted here, and there is a diagonal shifting, so you have two columns. And according to these two columns, you can again create a scatter plot, x, y, dot chart, yes, the chart with dots, and you can see the concentration of these values here around 0, yes. You remember that the development of one period, log returns, yes, this development was concentrated around 0, yes. The fluctuation around 0 was observed here, and also the development of these values in this scatter plot, scatter chart is like this. So it means that there is probably no significant dependence, probably no correlation, yes. We can move to sample autocorrelation function, which can be denoted AFC, autocorrelation function. We have here the formal definition, the sample log t autocorrelation of the time series is defined according to this formula. You can see that there is estimate of rho in time t, and this is equal to summation, through all t, and there we have multiplication. In one parenthesis, we have log return in time t minus the mean from log returns. And there is a log, yes, log return in time t minus tau, and it decreased by the mean calculated from log returns, yes. And in the denominator, there is a summation of these square differences between log returns and arithmetical mean of log returns. Yeah? So this is a formal definition for the calculation of sample autocorrelation coefficient in time t, but we are able to calculate a lot, yes, of these coefficients, a series, yes, of these coefficients, estimates of these coefficients. There is written where R with stripe, yes, is the sample average of the time series RT time series of our calculated log returns. Less formal approach if you are interested. Yes, this is not required. This is just illustration for you for your home study. As you can see, we have here I think 3 slides. Yes? So you will receive this presentation. So if you want, you can read it at home. So exercise 15, we can continue with other illustration on the data set. Sketch a graph of a time series with a positive sample log -1 autocorrelation. Sketch a graph of a time series with a negative sample log -1 autocorrelation. Use a real-life daily time series of close prices. So we will select some real data set and we will calculate the respective log returns. Calculate the sample autocorrelation function of log returns. I used a whiteboard, yes, and I draw these charts for you, like illustration, yes. So you can see on the top of this table the first graph, graph A, yes. We have written here in the legend no autocorrelation. Why? Because the points, yes, our values, observed values, are chaotically, yes, represented here without any system. Yes, there is no visible system of these values. The points fluctuate, yes, independently fluctuate around the x-axis. Yes. We can compare this chart, this graph, with situation B, which is written here in the middle. Yes, the values, yes, contains a system. As you can see that there is present a system. We can see a lot of values with positive sign. Yeah, there is a change. A lot of values with negative sign, and again positive signs and negative signs. Yes, and you can see that this is practically deterministic. Yes, there is a system of a lot of values with the same sign, yes, and change a lot of values with negative sign. So this is an example of positive autocorrelation and negative autocorrelation. The situation C, you can see regular, yes, regular changing of signs. Positive, negative, positive, negative, positive, negative, yes, the regular changing of signs, and then again, yes, we have the regular changing of signs, yes, positive, negative, positive, negative, positive, negative, and here there is also a changing of variability, changing of volatility, yes, in the time t. So on the bottom we have a typical representation of negative autocorrelation. And now the second part of this example, yes? We will use a real live daily time series. We will open selected close prices in EView software, and I will show to you the sample autocorrelation function. I opened here for you in EView software the close prices of Microsoft company. Yeah, so our well-known time series of 248 observations from 2nd January 2020 to 14th December 2020. So I have here close prices, yes, the development of close prices of the real data set, and according to formula logarithm from ratio, yes, close prices and close prices in time t-1, we calculated log returns, yes. So we can double click on these log returns and we can click on view button graph, and we can check what is here. Yes, there is a development of these log returns. You can see this conditional mean, which is around zero value. Yes, and our duty is to estimate the autocorrelation function, which is the function, the development of correlation coefficients. Yes, the development of correlation coefficients. So we'll click on view button, and we have here correlogram with 3 dots. Yes, so we will select correlogram of level, so we will estimate the correlation coefficients of values which you can see on this chart. Yes, so if you click on OK, you will see this table with 2 graphs and values. Yes, so first we'll check what is written in this first chart. Autocorrelation. Yes, there is a correlogram. Correlogram is a chart with correlation coefficients with columns representing the correlation coefficients. Yes, and the size of this column is the size of the correlation coefficient. Yes, if the correlation coefficient is positive, the column is to the right. If the correlation is negative, the column is to the left. Yes, so you can see these very small columns. Yes, here estimated values of these correlation or autocorrelation coefficients is written here. Yes, the values minus 0.094. Yes, is this value. Yes, and we can continue negative values, positive values, etc. Yes, you can see that the sizes, yes, of these coefficients are not so high. Yes, so we have here these correlation coefficients represented in the chart. Yes, in other different softwares, this chart, yes, is in the landscape format with values up and down. If the values are positive, they are up. If the values are negative, they are down. Yes, but in EViews, because there is also the table, yes, with these values, it's in column format. I opened for you another work file with data with close prices of Koffola company. So you can see here that I have opened another work file with calculated logarithms. Log returns of Kofola, calculated like logarithm of the ratio Kofola close prices and Kofola close prices in time t minus 1. Yes, so there you can see the log returns. We can open this file with log returns. So there we have the data, and again we can check the chart. Yeah? So please click on View, Graph, and you'll see line and symbol. There is a peak. Yes, you can see there is this observation 13 of March. Yes, 2020. Significant decreasing, yes. I don't know what happened on this day, but it doesn't matter. If you check this chart, you can see the same conditional mean around 0, yes. There is a 0 value and fluctuation of values around 0. So, as in the previous case here, in the case of Microsoft company, we can estimate the correlation coefficients, the autocorrelation function. We can estimate autocorrelation function. We can click on View, correlogram, and we will calculate correlogram of level. So you have here the results. Yes, the most important chart for us is this first one. Yes, now later we will speak about the second one and other values and functions in this table. Yes, but now at the beginning, enough for us is this autocorrelation chart, autocorrelation correlogram. Yes, the graph with correlation coefficients. You can see that, for example, on the first observation, there is a value of this raw correlation almost 0. Yes, you can see minus 0.007. Yes. On the second position, 0.091, etc., etc. So very small columns with 1, 2 exception, yes, on some observation, where is, for example, some significant change, yes, the peak up and down, yes. Maybe I forgot to say to you important thing. If this correlation coefficient, the column, yes, if this in this chart is significant, it's higher either on the right side or left side than the bound. Yes, you can see that you have here estimated 2 bounds. Yes, and these bounds, this line, yes, this bound is 95% confidence interval. So if this correlation coefficient is significant at 5% significance level, yes, is higher either on the right side or left side, yes, it doesn't matter, is higher than this toleration bound, yes. So you can see that in most of cases, yes, these coefficients are not higher than this bound, yes. So it means that they are not significant. They are not significant at a 5% significance level. But we will speak about this significance later. Yes. I will say to you something about the Durbin-Walson test. It's very important to say that this test is quite simple, because this test evaluate only the autocorrelation or the correlation between two neighborhood values. Yes, Durbin-Walson test is designed on testing autocorrelation of the first order only. Yes, only the first order. So it's not possible, yes, to evaluate the multiple correlation, yes, or more complicated correlation structure in the data set. Yes, but it doesn't matter, as we will speak about this simple approach, because it's programmed in most softwares. Yes, so Durbin-Walson test. It's necessary to note that all these tests, yes, all these tests have very often the same type of zero hypothesis. There is no autocorrelation. Yes, we will speak about other tests. Yes, and very often these tests have this zero hypothesis the same. There is no autocorrelation. The data is independently distributed. In our situation of Durbin-Walson test, there is no autocorrelation of the first order. Yes, so there is no correlation between all neighborhood values. Yes, observation in time t is not dependent on observation in time t minus 1. Observation in time t minus 1 is not dependent on observation in time t minus 2, etc., etc. Yes, autocorrelation or correlation structure between neighborhood values. Alternative hypothesis, there is autocorrelation. If zero hypothesis is rejected at the particular level of significance, there is autocorrelation. The test statistic designed by Durbin and Watson is calculated according to this formula. We can see that there is a summation through time t equal to 2 until the period t, the end of our analyzed time series. Summation of squared differences. Summation of squared differences between epsilon in time t and epsilon in time t minus 1. This can be, for example, a residuum or any other value. Yes, any other value, because Durbin-Watson it's not necessary, yes, to use Durbin-Watson test only for testing autocorrelation of the residual component. It's possible to use it on testing any data set, yes, not only the residual series. So squared differences, summation of squared differences between the neighborhood values in time t and in time t minus 1, yes. And in denominator, there is a summation of squared values epsilon in time t. Yes, epsilon t is residual in this situation. For example, capital T is the number of observation, the length of analyzed time series. And there is a distribution of these Durbin-Watson statistic. Yes, Durbin-Watson statistic is from range 0 and 4. Yes, we can see in this distribution some bounds. Yes, the fields, the partial ranges. Yes, we need to find in the tables which are designed by authors Durbin and Watson, the quantiles, the bounds, lower bound and upper bound, yes, and write these bounds to this distribution, yes, because you can see that there is position D lower and position D upper. And we can calculate 4 minus d upper and 4 minus d lower. Yes? And you can see that now we have here 1, 2, 3, 4, 5 fields in this distribution. If Durbin-Walson test statistic is close to 2, so inside this field, yes, there is no autocorrelation in the data set. Yes, no autocorrelation of the first order. If the Durbin-Walson statistic is close to 0 or close to 4, there is autocorrelation. Yes, we have autocorrelation in the data set. The data is not independent. Yes. In this situation, close to 0, we can say about positive type of autocorrelation. If Durbin-Walson test is close to 4, yes, we can speak about negative type of autocorrelation. And now about these two fields, yes, inconclusive. We cannot decide. Yes. This is some, we can say about, I don't know, the gray field, the gray zone, yes, where we cannot decide about autocorrelation, no autocorrelation, etc. Yes, so we don't know. According to level of significance, the size of the time series, number of observation, number of parameters in our model, yes, are these bounds different? Yes, we can find these bounds in the table. Yes, I talked about tables for critical values of Durbin-Walson test. We can, for example, use Google. Yes, and if you write to the searcher Durbin-Walson and you will select pictures. Yes, you can find some picture of the table. This is a print screen of any table. I don't know which level of significance, alpha. Yes, I don't know if this is 1%, 5%, 10% significance level, but you can see that we have here n, the sample size, yes, the size of our time series, and k, for example, number of parameters in the model, yes. And you have here, you can see that here we have here every time two columns, yes. So logically, the first column is d lower, yes, and the second column is d upper, yes. So if we really need to know the result, as we are able to find the tables and these quantiles. So I showed to you some table, illustration of the table, conditions that must be fulfilled of Durbin-Walson to be valid test. So constant term in regression, yes, so at least constant, yes. Regressors are non-stochastic. This test is not designed, yes, on data where is presented the stochastic trend or stochastic component. Yes, we will speak about the stochastic trend and analysis of stochastic time series later. Yes, so don't worry. No locks of dependent variable. So these three conditions must be fulfilled. Because the Durbin-Walson test has some disadvantages, we will learn another test. For example, Breusch-Godfrey test of serial correlation. Again, as I already said, in the case of Durbin-Walson, another test, zero hypothesis, is there is no correlation, there is no serial dependence, there is no autocorrelation, etc. Yes, so this is the zero hypothesis. Alternative one, there is autocorrelation. Yes, there is a serial dependence between observation. This test, Breusch-Godfrey test, is based on artificial, or we can say auxiliary, regression of residuals. Yes, this is a regression model which is based on analyzing of residual time series. We can use, for example, this simple formula where in many of cases we are using only this first part. Yes, epsilon, the residuum in time t, yes, is estimated like parameter of intercept plus beta 1 residuum in time t minus 1. Yes, this is the basic type, but we can extend this model by another parameters and another locked values of the residual time series. Yes, so it's a model, it's a regression model based on residuals, and if you establish the model on residuals, you will obtain after estimation new residuals. Yes, okay, so this is the model based on residual time series, and what can we do with this? Yes, if there is a system in the residual time series, if there is a correlation, if there is a dependence, this model is good, is quality. Yes, but we don't want this. Yes, we don't want to have a system in residual time series. We require independence. Yes, no correlation. So this model must be wrong, must be bad. Yes, very bad. So we are using either classical f-test or chi-square test to test the significance of the model. Yes, in many of softwares you can see the model, the regression model, the evaluation of this model, the test statistic of this model, and in some small table you can find the result of Fisher-F test or chi-square test for the testing of the significance of the model. And if this model is wrong, yes, non-significance of the model at alpha equal to 5% significance level means that there is no autocorrelation. So we require yes, the wrong model. And if this model is wrong, there is no autocorrelation. And we can continue. Yes, another test, Ljung-Box Q test. Ljung-Box test is again the test of serial correlation. It's very important to say that again we are using zero hypothesis, which claims that there is no serial correlation. Yes, there is no autocorrelation, there is no dependence, the data is independently distributed. Yes, there is written a formula for the white nose, as with finite variance. It's possible to calculate this Q statistic for the log, yes, log H. Q statistic for log H is equal to, N is the sample size, the length of our time series times n plus 2, yes, the size plus 2. And there is a summation from tau equal to 1 to h, as to some horizon, the length, as the maximum length, from this ratio. And we have here second power of estimated correlation coefficients, as, for example, in some time tau, yes, and this is divided by n minus tau, so the sample size minus this tau, this log, yes. This is a cumulative statistic. This is very important that this is a cumulative statistic. If you see the development of these statistics, yes, with h equal to 1, 2, 3, 4, 5, etc., every other statistic Q is higher and higher than the previous one. Yes, it's a accumulation, it's a cumulative statistic. This statistic has approximately chi square. It's approximately a chi square random variable with h degrees of freedom. So we are comparing these Q statistic with critical quantiles of chi square distribution. Yes. For a given h, this can be used for testing. Given h is horizon, yes, as I already said here. We have here written the zero hypothesis in a little bit different way, in statistical way, equality of all correlation coefficients, yes. The correlation on the first position is equal to correlation on the second position, yes. First correlation coefficient is equal to second correlation coefficient, and this is equal to third correlation coefficient, etc. So all correlation is equal, equality of correlation, so there is no dependence, yes. Everything is the same, there is no serial correlation between the values, yes. Alternative hypothesis, non-H0, there is autocorrelation in our analyzed data set. What else? I think that that's all. Exercise 16. For a real-life time series of log returns, in this situation calculated from stock prices. Yeah, they will calculate log returns from real stock prices. We will perform the hypothesis test for autocorrelation, the dependence in data in our data set. Breusch-Godfrey and Ljung-Box Q statistics. Breusch-Godfrey will be created like a model, yes, and Ljung-Box Q statistics are available in eViews software. Durbin-Walson test can be used only for a model, in a model, yes. If we have estimated the model and estimated the residual series, yes, on this residual series can be used this test, yes. So this one will not be used in this example, only Breusch-Godfrey and Ljung-Box. We have here again the same data set with close prices and log returns of Microsoft company, yes, and we will try to use Breusch-Godfrey test of dependence, Breusch-Godfrey test of serial correlation, the Breusch-Godfrey test, which is based on artificial regression. So we will try to create this regression model. Yes, if you remember, when we checked the autocorrelation function, yes, autocorrelation function and the correlogram, you could see that the columns of autocorrelation coefficients were very small, yes, and its values were below the toleration bound, so probably non-significant at the 5% significance level. But now we will try to calculate the proof of this, yes. So that is the window, yes, with work file. So please, we can click on quick button, yes, here, and there is estimate equation. So we will create the first model, as in our seminars we didn't create any model before, so now we will create the first model, yes. So you can see equation estimation, and there is command log. Very important, yes, for you. Dependent variable is followed by list of regressors, yes. So in this command log we must write on the first position the dependent variable of the model, yes. After we have a space, yes, and independent variables. So we will write here, if you remember, dependent variable is epsilon in time t, and in our situation we will use the log returns, yes, log return in time t, so we will write here log return space. We have here constant is c. In our presentation we have a beta 0, yes, or some parameter, some letter, yes, for the constant space, and after we had beta 1 and log returns or epsilon in time t minus 1, so locked value, locked dependent variable, so log return in time t minus 1, yes. So please write this to this command log equation specification. We are using least squares method, classical least squares, because this is a regression model, yes. The artificial regression created by me, for example, yes, by a statistician. So least squares and sample the whole sample, yes. So please click on OK, and there you will see the first model, the first result, which you can see in our seminar, yes. So our dependent variable log return, that is the model, yes. That is the model where you can see variable, constant c, and log return in time t minus 1. Coefficients. There is a coefficient of beta 0, and there is a coefficient of beta 1. Yes? So this is the simplest model, simplest Breusch-Godfrey model from our presentation. Yes? Okay, it's not important anything else in this model. We must check the evaluation, because this is the artificial regression, and I said that if this model is wrong, if this model is bad in the statistical way, yes, if this model is bad in statistical way, there is no dependence, there is no correlation, there is no autocorrelation, for example, yes. So you can see, for example, r squared or adjusted r squared here, and you can see that r squared is around 0, yes, almost 0, 0.00 something very small. So this model seems to be very bad, and Fisher F statistic is here. That is a Fisher F test, And we know that F statistic is connected with zero hypothesis. Model is wrong, model is bad, there is no significance in this model, and according to Breusch-Godfrey zero hypothesis, there is no correlation, there is no dependence, there is no autocorrelation. It's not important, it's not necessary, yes, to compare this F statistic with critical quantile, critical value from the tables, because we have here p-value, probability for F statistic, yes. Because this p-value 0.14 is above, is higher than 5% significance level, H0 is not rejected. What it means? There is no correlation, there is no dependence. There is no dependence inside the data set, yes? So according to this Breusch-Godfrey test of correlation, Breusch-Godfrey test of serial correlation, Breusch-Godfrey test of dependence in the data set, there is no dependence, and this is the proof, yes, that our previous test, Ljung-Box Q test, yes, said the same information. There is no dependence, yes? So we can move this on the left side, and you remember that we already had here another sample, another data set about Kofola prices and log returns of Kofola company. Yes, so we can create this artificial regression also here, yes, in the second sample, second case. You remember that also Kofola, yes, Kofola log returns did not contain a dependence, yes, there was independence in the data set of log returns, yes. So we will create the same regression model. So active is the right work file. We used quick button and estimate equation, yes. And here in this equation specification we will use the dependent variable log return Kofola, yes, it's the name, space. We will write C like constant, space, and we will use this dependent variable like independent variable, but in time t minus 1, yes. So we will write here log return Kofola and in parentheses minus 1, yes. We are using least squares method, so we can click on OK. And yes, it's necessary to delete this equation because it's not named, yes. So please click on yes. And we can check this second example. We spoke about the significance of the model, and we spoke about the significance, for example, of explained variability, yes. Do you know what is it R squared and adjusted R squared? It's a ratio of explained sum of squares on the total sum of squares. And please check here, adjusted R squared. R squared or adjusted R squared is from range 0 and 1, yes. And here you can see very interesting situation where adjusted R squared is negative, yes. There is a minus 0.00 and something, so it's absolutely nonsense, yes. So this model is wrong, and what it means, if this model is wrong, it is not significant, yes. Why? Because we have here Fisher F test, Fisher F statistic of the model, yes. The zero hypothesis in this situation of Breusch-Godfrey test says that there is no correlation, there is no system, yes, there is no dependence in the data, yes, and the p-value is almost 92%, yes, 92%, so it's above 5% significance level. It means that zero hypothesis is not rejected, so there is absolutely no dependence in the data set. No correlation, no dependence, no autocorrelation, nothing. Let's back to Ljung-Box Q test. What is it, Ljung-Box Q test? It's a test of correlation, it's a test of autocorrelation, it's a test of dependence inside the data set, yes? So again, we have here our two work files, yes? The first work file about Microsoft company and Microsoft log returns, and the second one, COFLA log returns, yes? So we will start with the first one, log returns of Microsoft company. So we can double click on this file where we have log returns, and again we can, if you don't see this table, it's necessary to click on view button, correlogram with 3 dots, yes, and select correlogram of level, yes, and you will see this correlogram which we already see, yes, before, with the correlation, autocorrelation coefficients, which you can see here. And do you remember the formula for the calculation of Ljung-Box Q statistic? I said to you that this Q statistic is cumulative statistic, yes? Cumulative. So every other value of this Q statistic in the time t is higher and higher and higher than the value before, because there is a accumulation, yes? And the Q statistics, according to formula which you could see in my presentation, you can see here. You can see that there is 2.22, 6.49, 7.619, etc. Yes, there is accumulation. Every other value, every next value is higher than the value before. Yes. So Q statistics. So autocorrelation coefficients, the correlogram with correlation or autocorrelation coefficients, calculate its Q statistics according to formula. And now, zero and alternative hypothesis. Zero hypothesis, in the case of Ljung-Box test set, rho on the first observation is equal to rho in the second observation is equal to rho in the case of third observation, etc. So equality of all rho, it means equality of all correlation coefficients. What it means? There is no dependence. Everything is still the same, yes? No dependence, no changing, yes, etc. And it's not necessary, yes, it's not necessary to compare these Q statistics with quantiles, yes, of the particle distribution. We have here p-values, yes, p-values. Zero hypothesis, there is no correlation, there is no dependence, equality of correlation coefficients, etc. If this p-value is higher than 5% significance level, zero hypothesis is not rejected. You can see that this is a specific situation. You can see that there is very small dependence between second and third observation, yes, but in all other cases, absolutely in all other cases, there is independence, yes. The first row is a test of correlation or autocorrelation of the first order, yes. Durbin-Walson, yes, if you remember the slide with Durbin-Walson statistic, which tests only the autocorrelation of the first order, yes. So it's independent, yes, and in all other cases you can see also independence, yes. So we can say that this is, for example, outlier, but there is probably absolutely independence in all cases, in all situations, in all observations, yes, according to Ljung-Box Q test. And we can do the same with the second data set, log returns of Coca-Cola company. So again, we can double click on log returns, and if you cannot see this chart, please click on view button, correlogram, and correlogram of level, yes, and there is almost everything clear. You can see this peak and this peak. Maybe you remember, yes, you remember the chart, yes, the development where you could see the changes, yes, etc. And on some observation, yes, you can see that there could be a dependence on the previous value, but in general, yes, in time series, we can say if you see independence on the first position, there is so small or no, absolutely no dependence in the data set that it's not possible, for example, predict, yes, these values. I hope that in the future we will speak about the white noise process, yes, white noise process, and this development, according to these results, yes, seems to be like we have here two samples of white noise, yes, two samples of white noise, which is absolutely non-predicable, yes, and there is no dependence, no correlation, no system inside the data. It's good to say here at least one notice that also exists, for example, runs test, yes, the test designed on signs, yes, plus signs, minus signs. This will be for self-study because it will be very difficult to show this to you in e-views. I will be able to show this to you, but probably you will not be able to train this at home, so this is a voluntary study if you have this opportunity, because it's necessary to download a special add-in to e-view software, and University Light Edition for students, which you have downloaded at home, doesn't allow to install this add-in. Yes. So about this runs test, run is a sequence of log returns of the same sign as, for example, positive or negative signs. Non-negative log return is denoted as plus, and the negative log return as minus. Yes, thus in following sequence plus plus minus, 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 plus, minus, plus, plus, minus, minus, plus, plus, minus, 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 plus, plus, minus. There are equal to 10 runs, yes? If n1 is the number of non-negative log returns, and n2 is the number of negative log returns for our data set, there are n1 equal to 9 and 2 equal to 10, yes? Thus the total length of our data set is n1 plus n2. Expected value, yes, something like mean, like average, yes, expected value and standard deviation of runs. Under the assumption of independence of log returns, the expected number of runs m and the standard deviation s of runs given the observed n1 and n2 in a data set of length n1 plus n2 r. That is denoted expected value ex and deviation sigma, yes? In one type of literature you can find m and s, m like mean probably, yes? Mean or average, yes, and standard deviation s like standard, but we know that deviation, standard deviation, is also the square root from the variance. The variance can be denoted dx, like dispersion, yes, dispersion of variable x, square root from the dispersion, yes. So expected value and the standard deviation, yes, expected value 1 plus, and there is a ratio. In numerator we have 2 times n1 times n2, and in denominator there is a summation, yes, n1 plus n2. And the deviation, standard deviation, there is a square root from, you can see there in numerator there is a small part from this formula, 2 times n1 times n2 times, and in parentheses we have 2 times n1 times n2 minus n1 minus n2. And in the denominator there is this part, yes, from the previous formula in squares, n1 plus n2 squared times n1 plus n2 minus 1, yes, and this all is below this root, yes, below this square root. If the number of runs in the first sequence is too small and suggests positive dependence, similarly, if the number of runs is too large and suggests negative dependence. A hypothesis test called runs test may be constructed in following way. H0, H1. H0, the sequence was produced in a random manner. What it means in different sentence, there is no dependence. Yes, the series is independent. Yes, or there is no correlation. There is no dependence. Yes, and alternative hypothesis, non-H0, the sequence was not produced in a random manner. Yes, it's not randomly distributed, so there is a dependence. If absolute value of Z statistic in different literature can be written U, but this is normally distributed, yes, normally distributed Z statistic. If this absolute value is higher than quantile from the standard normal distribution U 0.975, its value is 1.96, yes. So with absolute value of test statistic is higher than 0.975, then reject the null hypothesis at 5% significance level. We can continue with exercise 17. If you remember, we performed the hypothesis tests of autocorrelation, dependence, yes, in data, dependence in data set by Breusch-Godfrey and Ljung-Box test. Yes, Breusch-Godfrey test based on artificial regression and Ljung-Box Q statistics. Yes. And you can do this at home also by run test. Yes, we already talked about the run test. So you can train this at home, but only, for example, on 10 observations or 15 observations. Yes, the small number of observations of these log returns. If you remember, we have almost 300 observations in each time series. Yeah? So it will be quite difficult, but if you calculate this in Excel, I hope that it is possible and you will be able to do this. But if you want to train, yes, you can do this, for example, on 10, 15 values, yes, from this data set of log returns. So our results support the hypothesis that the log returns of a financial asset, financial time series, yes, are uncorrelated across time. Now, explore the autocorrelation in time series of squared log returns. Yes, so we will use log returns, logarithms of ratio price in time t and price in time t minus 1. And we'll use the squares, the second power, yes, of these values, and we'll explore the autocorrelation. For comparison, assess also the autocorrelation in time series of returns without logarithms. Yes, so just a ratio, price in time t and price in time t minus 1. Summarize the findings. What are the implications? We have here our two work files where we have the close prices and log returns of Microsoft company and Kofola company in year 2020, yes, daily data. And we will create the squared log returns, yes, of Microsoft and the Kofola company. So we have active this work file, and we can start with writing a keyword series. For example, SQ like squared, yes, log returns will be equal to log returns, and we will use the power function, the hat, yes, this function powered by 2. So enter, and we have here squared log returns. We can check the chart, yes, we can open the chart, so double click on this file and check these values. You can see that all values are non-negative, yes, because we use the second power, yes, and everything in squares is non-negative, yes. We can check the development, so you can click on view button, graph, and we will use line and symbol chart. As you can see that there is a 0, and the development, yes, is in this way. You can see the significant outliers, yes, if the change, either absolute, either positive or negative of log returns, yes, was large. If the change was large, the second power, as the square of this change, is much more higher. So there is the development of square log returns, and now we said that according to Ljung-Box Q statistic and the correlogram, yes, we will check the correlation structure if this data set is dependent or independent. Yes. So we can click on View button, we can check correlogram of level, okay, and we will see this result. So you can see the chart, the correlogram of autocorrelation functions, the values of values of correlation coefficient, autocorrelation coefficient raw estimate, yes, are here. The values are written here in this column, and the calculated Ljung-Box Q statistics are here. Yes, again you can see increasing values because it's a cumulative statistic. There is a series of p-values. Yes, we know that zero hypothesis is there is no correlation, there is no dependence. Yes, no dependence in the data set, and you can see small values, yes, below 5% significance level. So it means that this zero hypothesis is not valid at the 5% significance level. This zero hypothesis is rejected at this significance level. It means that the valid is alternative hypothesis. Alternative hypothesis, there is dependence, there is correlation, the data, yes, is correlated, the data is dependent. Yes? So we have here the dependence in this data set of squared values of logarithms. Yes? We will do the same with Kofola company. So we must create, yes, we must create square log returns of the Kofola company. So we will write the keyword series SQ log returns Kofola, yes, and equal sign, and we will write here log returns Kofola and the head, yes, the power function powered by 2. Okay, so here we have square log returns. So again, you can check, yes, this development. You can see non-negative values. There is 0. Yes, there is 0 because there was no change. Yes, and the second power of 0 is 0, but 0 is non-negative. Yes, so the development of non-negative values. Again, we can check the development view graph, and we will use the line and symbol. Okay. Oh, it's different. Yes, there was a period during March. Yes, during March of 2020. The development of significant changes. Yes. So this is the development of non-negative values of squared log returns, and we will check the correlogram and the results of Ljung-Box Q statistics. Okay, so there is the correlation structure, the development of correlation coefficients. Maybe one important notice, yes, because we have only non-negative values, you can see that the development of correlation coefficients is positive during all time. Yes, it's very interesting because all values in the time series are non-negative. We have here only positive values positive values of correlation coefficients. Yeah? So there we have autocorrelation coefficients, AC, Ljung-Box Q statistics calculated here, and p-values. Again, zero hypothesis. There is no dependence, no correlation, no autocorrelation. Yes, and on the first position, yes, you can see that on the first position there is no dependence, there is no correlation of the first order. Yes, this is interesting situation that there is no dependence, no correlation of the first order. It means that there is no dependence of neighborhood values. Yes, so the value in time t is not correlated with value in time t minus 1, etc. Yes, so autocorrelation of the first order. But there is a complicated correlation structure. Yes. If we compare the situation here with this development, yes, the zero hypothesis, there is no correlation, there is no dependence, yes, is rejected here every time, yes. So there is dependence, and here we don't have the correlation between neighborhood values. We will also use Breusch-Godfrey test of correlation. We have here the window, the work file with squared log returns of Microsoft company, and we will create artificial regression. We will use a quick button, and there we have estimate equation. And here we will increase the size of the font, yes, and we will write a regression model according to Breusch and Godfrey. So we will write here squared log returns, yes, squared log returns, dependent variable, yes, space c like constant, and square log returns in position minus 1, yes. So this will be the very simple regression model. We'll use least squares method on all samples. So please click on OK, and there is a result of the model. So we have here the C and square log returns coefficients. It's necessary to evaluate this model according to evaluation statistics and mainly the Fisher F-test of the model. According to Breusch and Godfrey, yes, the zero hypothesis is there is no autocorrelation, there is no dependence, yes. And we have here Fisher F-statistic and the p-value, which is below 5% significance level, yes. Because this p-value is very small, below 5% significance level, the zero hypothesis of Breusch-Godfrey test is rejected. So there is dependence, yes, there is dependence. So we can move this table on the right side, and we can open these squared log returns here, yes, and we can click on view correlogram, yes, there you can see correlogram of level. So this table, yes, this graph with these values. Again, zero hypothesis according to Ljung-Box. There is no correlation, there is no dependence. It's rejected in all cases. So again, here there is no dependence, no correlation, is rejected. So these two information, yes, is connected, so everything is alright, there is a dependence. Okay, so we can close these two windows and we can create, we can create another model, artificial regression according to Breusch and Godfrey. So we have activated this window, this work file. We can click on quick button and estimate equation. And we know that dependent variable is square log return scofola. We can increase the size, square log return scofola, and independent variables, yes, the list of regressors, constant, the intercept, space, and square log return scofola in t minus 1. Square log return scofola, and in parentheses we write minus 1. Again, we will use classical least squares method on all sample. Okay, so if you remember, in the case of Cofola company, we had no dependence on the first position according to Ljung-Box Q statistics. Yes, there was no correlation of the first order according to Ljung-Box test. Yes, so we'll check this result again. You can see that we have here r squared and adjusted r squared of this model. Again, very small, yes, very small r squared and adjusted r squared, and evaluation of this model is here on the bottom of this table. Fisher statistic. Zero hypothesis, there is no dependence, is not rejected at the 5% significance level. Yes, so the information which is here is connected with information of Ljung-Box test from the correlogram and Q statistics, but only from the first position. We will try one experiment. Yes, we can move this table here on the left side, and we will open square block returns of Cofola. Please click on view button, correlogram of level. Okay, and move this graph on the right side. Yes, so you can see, yes, there is no correlation, no dependence of the first order. We can try to improve this Breusch-Godfrey model. Please click on estimate button, and we will give here more variables. We can increase the size of the font, and we can copy this square log return scofola minus 1 and paste it here, and we will use second luck, and for example also the third luck. Yes, so we will increase this model. Yes, minus 3. Okay, you can see that there is a constant square log returns in first luck, second luck, third luck, and now there is 0 p-value. Yes, so the 0 hypothesis, there is no correlation, there is no dependence, is rejected on all levels of significance. So I showed to you the modification of Breusch-Godfrey test of the dependence. Yes, because here you can see that only on the first position, yes, there is no dependence, but on all other lucks Yes, there is a dependence. So the more complicated correlation structure. And according to this test, we can see that there is more complicated correlation structure. Yes, so it's good to use more tests every time. Yes, it's good to use a lot of information, connect this information, and decide. Okay, ladies and gentlemen, so this is the end of our fourth seminar. We talked about correlation structure, autocorrelation, the dependence in the data set. We talked about a lot of tests, so I hope that everything was clear, and on the basis of today's seminar, yes, we will continue and we will create another knowledge next week on the next seminar. Yes, so today's seminar is very important because on the basis of knowledge, this correlation structure, not only correlation structure, but the knowledge of dependence in the data set and analysis of dependence. Yes, we will be able, for example, to create the models. Yes, the particular models of log returns, of prices, etc. So that's all. I wish you have a nice day. I will see you next week, and bye bye.